Algorithms. Okay, so today's session I would be discussing Simon's algorithm or Simon's algorithm. Okay, so before that, there were some questions. I think it's better we discuss them uh, and go ahead. Okay, right. Yeah, there is one question here I see here by Lakshman Simha ji. Okay, can you please briefly explain about the quantum interference, how it is physically adopted in quantum computing? Okay, so the quantum interference. Okay, so we need to discuss that. Quantum interference. Okay, right. So before going there, we better see what are the things involved in this particular concept. There is something called interference is involved. I mean something interfering. Okay, and it is happening at the quantum level. So that's why it's called quantum interference. Okay, I see this quantum interference in two ways. So I urge the people also to see this two interference in two ways. Okay, number one interference understanding is type one is light interfering and interfering at quantum level for sure. Okay, and leading to leading to either enhancement or okay suppression. Okay, so what is this is the Young's double slit experiment. Okay, where a coherent laser source is there, the laser comes out the light, and if I have a double slit, okay, right, so light goes through both the slits. Let's say S1 slit 1 slit 2, and let's say other side of a slit I have a screen. What happens here is light coming from screen 1 goes hit the screen, light comes from the screen slit 2 goes hit in the opposite direction, means opposite phase. If they meet at the screen in opposite phase, out of phase, what I will see, I see a dark fringe there, a dark fringe. Okay, dark fringe is seen. Okay, let's say a light goes and hits within the same phase. In phase, I see a very bright fringe. Okay, so bright fringe is seen, right? So this is what the light being constructively and destructively interfering. Why is that so? If I just take a wave like this, let's say another wave which is of opposite phase. You see, because of the sum of these two waves, the disturbance or the resultant of these two waves is absolutely zero because both were pulling medium or anything, the energy in opposite direction at every point. They are out of phase. So the resultant of two out of phase waves, okay, is zero. So this is a destructive interference for you. If the light is the sorry, if the rays are traveling like this, okay, and they may need not be having the same amplitude. Okay, so they can be like this. Okay, see here both were in phase but amplitudes are different. But what is the resultant? Definitely some resultant will be there. What is the resultant? Let me show you. The resultant would be enhanced signal. Okay, so here this is resultant of in phase two waves, in phase two waves. Okay, so here what we see is a constructively interfering. You see, at this point they are meeting in phase wherever it is. Okay, so I can ensure that hitting the screen in phase two waves, they constructively interfere. So the constructive interference is like light gets enhanced at that point. So this is a double slit experiment where light interfere. Now, why is this only seen in the coherent source? Question is, why interference is seen, okay, with coherent light? Okay, if I ask that question, the answer is very simple. Only in the coherent light source only with the coherent light source, only with the coherent light source, we have properties like, okay, number one, the property is if I have two rays, if the two rays, if I well, by nature current light rays are all coming in a streamline. Okay, right? You can say they're streamline. But even for incoherent light also I can have streamline. So it is not a deciding factor, but streamlined light rays will be there. If I just take any two light rays, if we consider any two light rays, what is the deciding factor with them is, let's say there is a one ray like this, there is another ray, let me take with a different color. Okay, so there is another ray. Okay, now you see, when is these two rays are peaking? Let's say this is peaking at some later times compared to the first one. Okay, so there is a fixed difference. So like I say, you can say path difference. Let's say delta x. So okay, so both the rays will peak at the difference of delta x. So this delta x will remain for a very long distances. What I mean is, you are sending these two rays for a very long distance. This delta x of both peaking at the same time, be peaking, okay, they peak at different times, but what is the difference between the path lengths? Okay, this is always remains the same. So when this race goes to the next level and the other one also goes to the next level, sorry, okay, let me draw with the same color so that you people can notice that. Okay, you see the now difference. Okay, that remains intact. That exactly remains intact delta x. So that is the very important factor of coherent light source. This is a fixed path difference, or you can say, right, at any given point. Let's say now at any given point, you see. So this at this point, if you just notice, this is a fixed path difference remains. Okay, that is one point. Fixed path difference. Okay, right? So I can rely on these two rays. They always maintain a same property in the path as long as they travel. Okay, and there is a path difference. There is a phase difference also. What is a phase difference is, Okay, if we just notice at a fixed point, let's say this ray is increasing. Let's say this ray is increasing at let's say with respect to x-axis. Let's say the theta is, let's say, about 40 degrees Celsius, and the other one is, let's say, having an angle. What angle? Let's say negative angle. Let me take minus 40. Okay, so the first, the blue ray is rising. Okay, and the black ray is not rising in a clockwise, anti-clockwise. It is rising in a clockwise direction, minus 40. So what is the path, what is the phase difference between them? The phase difference between them is, the phase difference is about 80 degrees Celsius. 80 degree phase Celsius. You go to any point in this race, let's say here, there also it is rising by 40. The other one is going down by minus 40. So there also 8. So the fixed path phase difference also maintains, okay, for a very long times. So these are the deciding factors whether the light rays are coherent or not. Path difference and the phase difference. Obviously, they are coming from saying coherent light source, they have a fixed path of wavelength, fixed frequency, all those things are there. Path difference and phase difference are the ones which are very, very important. So because of these factors, I see when these two rays coming and hitting at a point with the opposite phase, they destructively interfere. When it comes to coherent light source, right, I gave an example. Okay, the rays would be of equal amplitude and equal frequency. Okay, so we don't see this kind of an effect with the incoherent light source. We just see the effect like this. They may destructively interfere or they may constructively interfere because all are of like rays. So just to show you how the out of phase, sorry, in phase things will work, I gave an example of this colored rays. Okay, so the having coherent light source is important to have constructive and destructive interference. Okay, that is one of the property of coherent light source. Now coming back to the name quantum interference. So this interference of light rays happening at the quantum level means photons are interfering. So you can term this as a quantum interference. Okay, right? So what I see is, let's say, one ray, if you take it as some x ket, okay, another ray you can treat it as some y ket, both will interact and they may add up and give us 0, and they may add up and may give us some height. Both possibilities are there. We can term them as a constructive, or we can term them as positive enhancement or opposite enhancement giving 0. Okay, right? So that is how I connect to the quantum computing here. And there is another way of also saying the actual quantum interference. No, I'll not say actual. The physical interpretation goes inside is very, very intuitive. What is that is quantum interference. You just consider three level atomic system. Three level atomic system. Okay. So this is very important for the case of lasers or anything. So let's say I have a three level atomic system, 1, 2, and 3. 0 ket, 1 ket, and 2 ket. So now we can arrange this three level atomic system in two fashions, or three fashions, I might say. All right. Depending on how my input signal is, okay, accordingly I can rearrange. That is the beauty of a three level atomic system. Remember, depending on the input signals, we can arrange, okay, or consider this three level system, three levels Okay, in different configurations. What are those configurations? Let me show you. Number one, lambda arrangement. What is the lambda arrangement? Is 0 ket, 1 ket, and 2 ket. How it is lambda? Lambda is capital lambda, so it is written like this. Okay, right? Mid level I just push it to the right, and top level I push it to this little bit right. So what I am doing here is there is a difference between ground to excited. There is a difference between excited, first excited, second excited. Just for the convenience, I put 0 kit and 1 kit very close to each other. It is possible of that kind of an atom. So this is a lambda type configuration. There is also one more. What is that? Is V type configuration. 2, 1, and 0. Okay. So here it's a V type because, so this is what V type. So this is a quantum optics for you. Okay. Now, whatever we just took it by default, it's called a ladder type configuration. And who decides which one to take? The way your my signals, input signals are interacting with this atomic system, that will decide. Now, the way people take is they take, let's take a lambda system. Let's say I have a lambda. Let's say equally spaced, but for my own convenience, I have took them separate at different. Okay. Now I have a laser. Let me call it as a pump. Okay, let me call it as a pump laser, pump beam they call, which has a energy matches with the 0 to 2 transition. Okay, so angular frequency of the pump. Okay, it matches. Now, let's say I have a probe, another angular frequency of the another laser source, which is, let's say, probe, omega probe. Okay, this is what I have, right? Now, using a pump and probe, what I can do, whatever atoms, electrons at the ground level, okay, I can push them complete like a maximum to level 1 by what? One electron from the 0 to 1 is pushed with a pump, okay? From level 2 to level 3, so level 1 I can push with a probe. So maximum number of whatever is possible, they will go to level 3. And I can ensure that for the time being, from level 1 to 0, I can somehow remove it. Means I can stop that decay. So what I am doing, I am creating large number of atoms accumulating at the level 1. Okay, this is also called population trapping. Okay, using two light rays as a laser source, 3-level atomic system in a lambda configuration, you can trap the electrons at level 1. So how it is happening here is, okay, so direct. Now there is a way also I can stop such trapping. Okay, there is a way I can stop electrons going to level 1. Okay, and electrons, if at all if there is any electrons in 1, they may be pushed back to level 2 and level 0. That is also possible. How is that is possible is, okay, if there is any transition happening to level 0 to level 2 and then level 1, that will be completely suppressed. How it is suppressed? Okay, so when I take a 3-level atomic system, if I have a 2 lasers, electrons going to level 1 can happen in multiple paths. Okay, there is only one path you see here, there is a multiple paths. So whatever paths you showed is path 1. There is another path also, and it's very interesting if I showed you that path is electron will go directly to the level 2 and comes down to 3 1, and again it goes back to O2 and then comes back to 3. So select back to 1. So it makes one circle between 2 to 1 and then stops at level 1. So if I just say this is a path 2, so the possibility of reaching orbital 1 or the state 1 from 0 is there are two paths I showed you. There is one more path also is possible. What is one more? Instead of making one circle, it makes two circles. Okay, right? So this is one more. Let me call it as a path 3. How many such are possible? Paths are possible? Infinitely many. Okay, but the initial ones are most dominating. Later ones are becomes lesser and lesser dominating. So what happens is all these paths together interfere. Let's say it's like all the players they try to impress their presence by putting the electrons from 0 to 1 through 2. But the thing is, sometimes they may interfere destructively and they may not able to even show any kind of a change, any kind of a difference, because they're all fighting with each other. So when they're all fighting with each other, we will say all the paths are getting interfering and they destructively interfere all the paths from 0 to 1 via 2 destructively interfere. So that is called quantum interference for you, and leaves no electrons at level 1. So basically I am creating some kind of a null orbit where no electrons would be there, a null state. Okay, so this is possible because of the transitions of electrons between the levels are interfering. You see now the interference is between the transitions of the electron, transition paths. So that is a quantum interference for you at a experimental level or in the experiments. But what kind of interference we just saw so far? Light being interfering and giving a positive or a zero effect. When it comes to experiments, the transition of the electrons between the levels, any two levels. Now you see, transition between 0 to 1 only I am talking. It may happen with via another level, but my ultimate goal is to reach level 3, level 1 from level 0. So these things will interfere and sometimes they enhance, sometimes they destructively suppress. Okay, so this is the actual quantum interference terminology and the concept for you. When it comes to quantum computing, okay, let me explain. The quantum computing, okay, involving interference. Okay, now let's say I have a numbers. I have a numbers. Let's say I have numbers. Some x is given as 0, 1, 2, 3, so on. Let me write down fully 5, 6, 7, 8, 9. I have 10 numbers. I have wrote on the paper, so you can see them. Let's say I write them on a cube, and each cube number is written, and just put it in a basket, okay, or a basket. And you are not able to see, but one information I would be giving you is there are numbers inside the box or a basket written from 0 to 9. There are 10 numbers. Now I'll give a task to pick number 7. Okay. So number 7 is having a property like a prime. Okay. It doesn't have any other factors other than itself or 1. So such a prime number it is. So I have to pick, or you have to pick that number. That is a task. Okay. But here, if I ask a person to do it, he may do it randomly. Okay. Right. And on his lucky day, he may get it in first attempt, maybe second attempt or a third attempt. On his worst day, he may get in the last attempt, that is 10th attempt. Okay, right? Unless whatever he picked, he put it outside. In that case only, I'm telling. Let's say he picks, if you don't find, he put it back in the basket. In that case, on his worst day, he may not pick at all. Okay, that problem is there. Anyway, but we are thinking that whatever he picks and put it outside, in that way he picks a number 7. Fine. Now, the question is, how many number of attempts required for me on the worst day? 10 attempts. N equal to 10. So 10 attempts are required. Provided I remove the each time whatever I picked, put it outside. Okay, right? Now, is there any way I can reduce the number of attempts to less than 10? Yes, using some classical algorithm, there is a possibility. Okay, but the question is, I want to reduce to much less. How? How I can reduce? It's a very simple. Somehow I put them all the 10 numbers in the form of a quantum superposition state. Okay, let me call it as a quantum state psi, which will have a0 0 ket, a plus a1 1 ket plus a2 2 ket, and so on, a9 9 ket. So the input information, given information, I convert into quantum states. Okay, convert given data to quantum information, that is superposition. Now I know 7 is lurking somewhere inside. Somehow I have to pick that using some quantum algorithm. What quantum algorithm I would be needing? I would be needing a quantum algorithm. Okay, let me show you. Okay, so you just see the amplitudes associated with each number is there, a0, a1, a2, a3, and so on. Let's find out the probability by taking absolute square of the amplitudes. Okay, so let's plot those amplitudes. Let's say for the 0 ket there is an amplitude, for 1 ket there is an amplitude, 2 ket there is an amplitude, 3, 4, 5, 6, 7, 8, 9. Okay, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for the way I have arranged my data is such a way that all of them are equally probable. Obviously, right? When I have inside a basket, 10 cubes are there. Picking any one is of equal probability. Okay. Now I want to pick the 7, the cube with 7. Somehow, what should I do? I should enhance the probability of 7 to higher level and suppress the probabilities of the other ones less than what it was there initially. Okay, so that is the target I want to do. What is the target I want to do? I have to enhance the probability of 7 and suppress the probability of other things to lower values. So what I have a possibility to reduce a0, a1 up to a9 except a7. A7, A7, okay, we have to increase. Okay, A7 to be increased, but AIs except A7, all of them must be decreased. That is the requirement for us. So, by using quantum interference, by ensuring the interference between each other number, we can destructively interfere the probability amplitudes of each one. For example, the A1 and A2 can be interfered destructively and reduce their amplitudes. A2 and A3 can interfere destructively and reduce the amplitude. Okay, so but interestingly, A7 can be made A7 and some other number, let's say A5, constructively interfere, but the thing is A7 gets increased the amplitude, but A5 will not increase the amplitude. So in that way, what we can do, I can create a possibility to improve or increase the probability amplitude for a number I want to pick. Okay, so that is the constructive interference work as per my wish. So that is the quantum optimization or quantum algorithm for you, which is in fact this will be this will be this is actually, it's not will be, it is the actual working principle. This is the actual working principle, okay, in Grover's algorithm, right? So what Grover's algorithm does, somehow the required number, its probability amplitude is increased. All other numbers which I don't want, their probability is suppressed, right? So this is the quantum computing application where the interference is being used. See, the effect of interference is a usually it appears to be a experimental event, but even for the computing it can be used. So that is the answer for the question being posed by Narsimhaji earlier. Okay, I hope I answered your question. If you have listened, please respond how it is physically adopted in the quantum computing, in the labs, or in the computing. Okay, right? So, fine. Okay, then. So, let's go to our business straight away, which is Simon's algorithm. Okay, right. So, the Simon's algorithm, it's like an extension of, it's an extension of what our yesterday discussed Burston's-Wadrani algorithm. Okay, right. So let's see what is the Simon's algorithm is. Okay, I have some visual impact creating first slide. Okay, so it says it is given by Daniel Simon around 1994, but it came to limelight in 1996 onwards. Okay, and what it says, it is the first algorithm that provided the quantum advantage. Okay, very nice. Okay, and in a way it given a foundation for modern quantum algorithms, right? Okay, so there are some facts with respect to the Siemens algorithm. What are the facts is it demonstrated an exponential speed up. Okay, right? And how exponential speed up when it comes to classical and quantum. Okay, demonstrated exponential speed up, right? And okay, and if a problem is artificial but mathematically clean, it's designed to expose what quantum computer can fundamentally better offer. Hmm? Okay, so in fact, the Siemens work directly inspired the Shor's factoring algorithm. The Shor's algorithm is another algorithm which actually revolutionizing as of now. Okay, because the Shor's algorithm is creating a big threat to existing RSA encryption. Okay, right? So this algorithm again operates on a same basis as Dutch JOISA with a Oracle. Okay, Oracle or a query model. Okay, where the complexity is measured by the number of function evaluations which we will be making. Okay, right? So that let's see in the later slides. I have just a block sphere interpretation just for the in and just like just for the appealing I added. Okay, so what is this Simon's algorithm is? Okay, right? So it let me explain using a, a text. Simon's algorithm. Okay, so what so far we were doing, we are understanding any algorithm by considering, okay, by considering like a two parties, Alice and Bob. Okay, now there are two people, they want to communicate, or let's say they want to create a quantum channel where they can to communicate. Okay, let's say Bob uses some function just like Dutch Joyce algorithm. Bob uses a function f of x. What kind of function is this? Okay, it's a function which takes a set of inputs. Sometimes I write tensor n. People don't use tensor n. Okay, but it's better to use one. But if it is not there, you can think that. So it's a function is between computational basis to computational basis. Okay, it takes the input values and gives you output values. Fine. Now earlier we saw the output of function is 0 or 1 in the case of 0 or 1 in the case of Dutch Joyce algorithm or Bernstein's-Fujitani algorithm. So this function is slightly different from what the function being used there. So this function is, it takes a bit string as an argument as an x and gives away the function value also as a string. You remember that. That is a main difference. Okay. Now that is a function. Now it's not only that, it is more than that. What this function also satisfies is this function values for some input arguments are going to be same, obviously, right? Okay, even though they are the bit strings, the output, they are going to be different. Sorry, going to be same. What I mean is, let's say there is a x comma y belongs to 0 comma 1 tensor n. Okay, for any two values or some two values, there exists some two values. For that, we can write up there exists symbol. There exists x comma y belongs to 0 comma 1 tensor n. For that, f of x is equal to f of y. And one more thing is, there is an interesting relation exists between x and y. What is that interesting relation is, if you add x to y with addition modulo, you are going to get some s. Or you can also say that as x is equal to y addition modulo s. Okay, right? You remember, you add any number on the right and left with addition modulo you can do. Okay, so you get the any of this equation. So it's important to note that both of them are same. Okay, now see, s is a bit string again. S is a bit string. So this is kind of a function Bob is using. Okay, so this function is this function is described by, okay, this function is described by s. Very, very important. Okay, let me conclude that. So most important thing is s describes this f of x. Okay, now the question is, Alice has to find out the task of Alice is to find what kind of f of x is that. Find the f of x. Instead of finding f of x, she can do one thing. She can find, that is, she can find the s. Okay, either way it is same. If she finds f of x, she will get s. If she finds s, she can get to see what is f of x. Okay, now how, okay, now the process. She can ask Bob directly. Okay, s is a bit string, means let's say it will have some, okay, if s is, let's say having s1 s2, let's say sn, it's a bit string of length n. So the process would be, Alice can ask bit by bit, okay, to Bob, okay, and find the s in how many steps? In n steps or n queries. So what is the number of queries required? Let's say n queries are required, right? So this is again, now the question is, how Alice can find the s being used by, or the f of x being used by Bob in a very less number of attempts or queries. Okay, so classically, can we reduce, or using quantum computing, can we reduce to much smaller case, smaller number, very very smaller number? So that is the question, right? So the final question is how to find s in less number of queries using classical algorithm or classical processes. And further, reduce the queries to very low, very low using quantum algorithm. Okay, so those are the two things we would like to answer today, right? So again, just like what we saw last time, Burst's Vajrani algorithm is going to help us to find the quantum error correction doing, or it help us to do some quantum cryptography. In a way, Siemens algorithm could also be in a same direction. It can help us. Okay, right? So now it's 3:56. We will just take a 5-minute break, and then we'll come back and we'll answer the questions which I just posted here. What you do is just stare at this for 5 minutes and have a sip of water, and then when you come back, we'll understand that. Okay. Yeah. Hello. Welcome back, everyone. Yes. So, yes. Right. So, let me come back on Simon's algorithm and explain with a specific examples. In that way, people understand much better. Okay. Right. So, yeah. Right. Okay. So, the Simon's function is f, which goes from 0 to 1 tensor n to 0 to 1 tensor n. Okay. Okay. So there exists x comma y belongs to 0 comma 1 tensor n. Okay. For that x comma y, f of x is equal to f of y, and which is given, okay, that x is equal to y with addition modulo s. Okay. Where s is again belongs to 0 comma 1 string n. Okay. Right. So this is the function, and let's understand this using a simple example. Okay. The example which I would be taking is, I'll take a n equal to 3 case. Okay. N equal to 3. Right. For that, what is my x would be? X would be, okay, for example, let me take few examples. So n equal to 3, what are the possible x values I can have? It will be 3-bit string. Okay. Okay, so let me have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay, right? And 1, 0, 1, 1, 1, 0. Okay, and what else? 0, 1, 1. Okay, and last one is 1, 1, 1. Right? So I have 0, 1, 2, okay, 3, right? And 4, 5, 6, 7. Have I missed something? 001, 010, 1100, 101, 110. Okay, right? Uh, yeah, I have not missed anything. Okay, so I have 8. Right? So there may be a binary misalignment, but don't worry. So I have 8 numbers here. Okay, right? So, uh, okay, let me change it as per the requirement. It's better in that way. So 001, 010, 011. Okay. So it's better 011, right? And then 100 and 101 and 110. Makes sense now. Okay. Now these are the argument x value. So these values goes into the function. Let's say it gives me some values. So this is the values. I'm not making out. Let's say there is a function which gives me taking triple zeros bit string and gives 101. There is a 010, 000, 110, right? 000, right? 000 and 110 and 101 and 010. So this is the okay. So this is the values which goes in and comes out. Okay. For example, here, let's say I feed. This is x0, x1, x2, x3, x4, x5, x6, x7. Okay, if I feed x0, which is f of triple zeros, goes in and gives me 101. That's the bit string I'm getting. So if you notice from the table, I have f of, okay, so where else? So there's a 101 is coming here and also here, right? So what is that? x6 f of 110 is also giving me 101. Is there anywhere else? No. So two output values of the function, okay, is same. So basically what I'm saying, f of x0 is equal to f of x6. Now x0 and x6 are different. What are they? They are triple zeros and 110. Okay. And the thing is, there exists a s. What is the s? S has a form which is actually x naught plus x6 is actually s. Okay. Or you can say, right? So s here in this particular case, s is okay. So s is 110. So if I add s to x naught, it is going to give me x6. Let's see that. Okay. So what is the x naught? What is the x naught? X naught is triple zeros. What is the s? S is 110. Let me add bit by bit 0, 1, 1. So that is what is my x6? That is giving me x6. Okay. And you can also check the other way around. Other way around is take x naught, which is 110, add s to that. That is 110. If you add 0, 1, 1, 1 plus 1 is 0, 1 plus 1 is 0. You don't you don't carry here. You can simply put the sum with addition model. So I am getting x0, right? So S is such a bit string. S connects the numbers or the bit strings which are going to give me same functional values. Okay. Now the question is finding the S for a given f of x. Okay, right? Question is finding. That is what we want to do. Now, probably if you see among the f of x values, okay, let me see, there is two numbers common, same, okay, right? So even for there is a 0, 1, 0, right? So f of x1 is equal to f of x7, which is 0, 1, 0. Another pair. Let me round with another color. Okay. And what else? Do I have any other? Yes, there is many. Okay. There is one more. What is that one more? There is a 110 and there is 110. Okay. So what is that? F of x3 is equal to f of x5. What is the value? 110. Okay. And also, let me take one more color. F of, okay, this color is not appearing. Let me take here. F of, okay, x4 and x2. F of x2 is equal to f of x4. What is the value? Triple zeros. So, along with f of x naught is equal to f of x6 being, what is the value? 101. Okay. So there are other three pairs here. Among the 8 pairs, sorry, among the 8, Okay, here if you see, among 8 x values, there are 4 pairs giving same f of x. Okay, right? So classically what you can do, right, what you can do is you can just see from the list, okay, right, and find out which two are giving same functional values. Okay, right? So right now you are seeing on the paper, right? If at all, if I had to write the program, what program can do is program can pick any two of them, okay, any two of them, find out f of x value. From the f of x value, if it succeeds, okay, if two f of x values are same, and then it immediately go and calculate the s value by just summing the x x x argument values which are giving the same. Let's say what I mean is, okay, the process. What is the process? Could be classical process. Find the xi and xj for which f of xi is equal to f of xj. Very simple. Add xi to xj to get s. Okay. Let's say while picking xi and xj, in a first attempt, somebody fails to find the equal values of f of x, which means you have to go to the next pair. Okay, right? So, how many attempts are required? Now, question is how many attempts required? Okay, right? So let's say I take a first xi, then from the remaining I need to pick one more. Okay, to pick one more. So it's like, let me name them. Let's say first one is Alice. Alice is picked. Alice has to find a Bob from the remaining list who is going to give us same functional value along with the Alice. Okay, right? So now it has become a combinatory problem. Okay, so for every guy there is a n minus 1 guys available. Okay, so for every guy Alice has to pick Bob from the remaining list. Okay, if there are n x's, then okay, how many attempts? N into n minus 1 attempts would be needing. We need to check. What I am saying is, let's say Alice go and pick one guy, is not Bob, so she has to leave. She has to go to next guy. She checks whether the Bob is there or not. Okay, right? So n into n minus 1 attempts are required. But the thing is, you see now, okay, right? So this many to pick Alice and Bob pair. This many attempts are required. Remember one thing: if a Bob and Alice pair is also same as Alice and Bob pair, so which means not n minus 1. I would be needing n into n minus 1 divided by 2 attempts, because permutation Alice and Bob is same as Bob and Alice. Okay, so this many attempts are required. Even okay, as per the permutations and combinations, okay, this will be nc2, which is n minus 1 divided by 2. Okay. So this many attempts are required. Now, overall, what is the order? Order. Therefore, the order of attempts or queries is, okay, n square. N square attempts are required. Classically, to find out the function and the s, okay, right? So you may not succeed in the first pair, you have to go to the next pair and so on. So you would be needing n square attempts, okay, right? So when it comes to quantum, you can reduce this, right? It's a quantum query complexity. So there, what we would be using is, we would be using a quantum algorithms, okay? So you quantum algorithm, I would say quantum circuit would allow to reduce the order n square to lower values, lower level. Definitely. It's very, very important. How? We will be just using the same as a Dutch algorithm kind of a circuit. Okay, where the circuit would look like, do I have a circuit in my PPT? Okay, just a minute. Let me directly go to the block box. Yeah, I have a circuit here. Okay, so what matters here most importantly, okay, it is just like a Dutch algorithm where all the input x values would be taken as equally probable by taking Hadamard's n Hadamard's. Now please mind here, the n stands here for number of qubits. Number of qubits means, what is the data size here? N is the number of qubits. The data size for us is 2 to the power of n is the data size. Okay, right? So 2 to the power of n bit strings. If it is a 2 qubits, the number of bit strings is just 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1. These are the four possibilities, four data points. Okay, if it is a 3 qubits, we just saw earlier, we'll have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, and 1, 1, 1. So this is for 3 qubits. If it is for 4 qubits, you can imagine. So it will goes on like that. Okay, fine. So in our case, it's 2 to the power of n data size means n is number of qubits. Okay, one of them would be, if you want, n qubits. One of them would be 0, 0, 0. How many zeros? N zeros. That is one state, one bit string, and so on. The next one, 1, 1, so on, 1. So n ones. So this is 2 to the power of n bit strings. Okay. Now quantum circuit is 2 to the power of n data points were initially put in. Okay. Sorry. Initially, sorry. So initially n data points, n qubits were all taken in 0, and then we'll have a Hadamard gate. Okay. And then I will create the equally superposition of 2 to the power of n bit strings. So this is 2 to the power of n bit strings were created with the Hadamard gates. And the next, we'll have a query also slightly different from what we had in the Dutch and Dutch JOISA and also Siemens algorithm. The query is n bit strings. All are in 0. So then we'll have a oracle, a quantum oracle, which helps me to find my function. Let's say somebody uses function. I can find that function by using a oracle. Now query part again goes through Hadamard gates, n Hadamards. Okay. And then I'll have ancilla goes as it is. And I'll only make a measurements at the query part, just like we did for the case of Dutch-Joyce algorithm. Okay. So by studying the output at the query, we will find out, okay, what is the yes. Now, if I have to write down the quantum state level by level, quantum states. So there is a level first Q0, so sorry, psi 0, psi 1, psi 2, and psi 3. Okay, right? So let's worry one by one, level by level, what we are going to have. Okay, like the first one, psi 0 is very simple. Straight away you can write n qubits tensor, n ancilla qubits. Okay, now what is the psi 1? Psi 1 is n Hadamards acting on the query. Okay, and identity, nothing is acting on the ancilla. Okay, so now last time we just saw, okay, for your own convenience, let me show you. Okay, right, a Hadamard acting on 0 gives me what? 0 plus 1 divided by square root of 2, which is equals to proportion, which is plus ket. Okay, and H acting on 2H acting on 0 is, okay, I'll be getting 0 plus 1 divided by square root of 2 tensor 0 plus 1 divided by square root of 2. So what is this? This is 0 0 0 1 1 0 plus 1 1 divided by 2. This is what I get. Okay, by the way, you can write this as plus ket tensor square. Okay, so you just take this analogy, which means similarly generalization, H tensor n acting on this is plus tensor n. Okay, so that's what I'm going to write here, plus tensor n tensor 0 tensor n. Okay, now this is what I have at the psi 1 level as per my quantum circuit. Now I want to find what is the psi 2. As you can see, it's a function Bob is using. Let's say Bob is using, Alice has to find. Okay, if Alice supplies some x value, Bob finds the x value, okay, or processes the functional value. You will only give the function values to Alice. Okay, so for that, okay, the way we will write is the quantum Fourier transform function acting on any query with an ancilla, okay, is going to give me the ancilla being replaced by addition modulo of function value of x. Okay, this is a function Alice's Bob is using. Okay, let's say specific case, specific. If a is 0, okay, in that case, a is 0. In that case, what happens? Fourier transform function x acting on 0 is x comma f of x plus 0, which is simply x comma f of x, right? And remember, this can be generalized. generalized to any order. I just gave only for one qubit, one ancilla qubit, one query qubit, but I can do this for anyone. What is that? We have our psi1. So our quantum Fourier transform function acting on our psi1, which is quantum Fourier transform acting on, okay, right? So let me write down specifically. What is that? Plus ket tensor n, 0 ket tensor n, okay, right? So now plus ket tensor n is also written in a different way. What is that different way? Right? So let's see here. Plus ket is written as summation over x belongs to 0 comma 1 tensor n x ket divided by square root of 2 to the power of n. Okay, where n equal to 1. Okay, for a plus ket. If I have to write a plus ket tensor n, I'll have summation over x belongs to 0 comma 1 tensor n x ket divided by 2 to the power of square root of n for any n. Okay, so I have it here. Let me write down. Fourier transform function acting on summation over x belongs to 0 comma 1 tensor n x ket divided by square root of 2 to the power of n 0 ket tensor n. So why did I change? I want to have this kind of a interpretation. Okay, so let me write down that. Now what is the psi 3? Sorry, what is psi 2, right? Psi 2. What is the psi 2? Psi 2 is, okay, psi 2 is summation over x belongs to, this can go directly here, x belongs to 0 comma 1 tensor n 1 by 2 to the power of n. You can keep the summation, sorry, uh, fraction outside. Fourier transform x ket 0 ket tensor n. Okay, now what is the answer? Answer psi 2 would be, right, 1 by 2 to the power of n, okay, summation over, and if you are not comfortable keeping outside, you can keep it inside if you want. Let me put it inside only. X belongs to 0 comma 1 tensor n, okay, and what I will have here is x ket f of x ket, so simply getting replaced. Okay, right? So now you see psi 2 I got. Okay, this psi 2 is slightly different from whatever psi 2, sorry, Fourier quantum oracle function acting on this, slightly different. This is for n equal to 1 and this is for any n, for any n. Okay, now if you carefully look at this, this is an entangled system. Entangled system. How? Okay, how this is an entangled system? Let me explain. Explanation. Okay, right? So if you notice our entangled circuit, which is Hadamard gate followed by CNOT. Okay, right? This is like oracle box. This is like quantum function. Now you see, this is 0. Here I have 0 plus 1 divided by square root of 2. This is 0. What is the output? Output is 0 0 plus 0, sorry, 1 0 1 1 divided by square root of 2. This is a Bell state, entangled state. Okay, so that is what we have it here, right? So remember, this is a bit string and this is also bit string. Okay, right? So together they create an entangled pair. So interestingly, that would help us to find the S. Okay, so what we will do next is, okay, so as per the circuit, now I got a site. What is the circuit? After the site 2, I have a Hadamard's acting on query part of the site 2. Okay, right? So let me find out site 3. Site 3 is Hadamard's, n Hadamard's, and identity acting on, okay, site 2. By the way, site 2 is this. Okay, so specifically if you want, you can write down site 2 would be, okay, okay, let me write down. Then it is easier to take it inside. Site 2 is summation over x belongs to 0 comma 1 tensor n 1 by 2 to the power of n x and then f of x, right? Yeah, now this goes and acts on this and this goes acts on this. Okay, but by the way, yesterday we have also derived one more thing. What is that one more thing we derived is h acting on any x is equal to summation over z belongs to 0 comma 1 minus 1 to the power of x into z, z kit. This relation we derived. Okay, if x is a qubit string, okay, one input, it can be 0 or 1. If x is 2 qubit bit string, 1 qubit. If it's a 2 qubit bit string, I'll change the right hand side. What is that? For 2 qubit bit string, okay, so I'll have 2 Hadamards acting on x, which is summation over z belongs to 0 comma 1 tensor 2 minus 1 to the power of x dot z, z kit. Same. Only thing is this time I'll have tensor 2. Okay, generalization for n qubit bit string. Okay, what is that? N tensor acting on x, where x is a n bit string. I'll have z belongs to 0 comma 1 tensor n minus 1 to the power of x dot z and z. Here you remember z is also n bit string. Okay, which means what is my psi 2? Psi 3. Psi 3 would be summation over z belongs to 0 comma 1 tensor n and summation over x belongs to 0 comma 1 tensor n 1 by 2 to the power of n. Okay, in place of x, okay, in place of x I'll get a z, which is z cat. Okay, before that I'll have minus 1 to the power of x into z, okay, f of x. Okay, right? So this is what I have it at the psi 3. Now the psi 3 we will analyze. Okay, so if you analyze psi 3 and find out what is the S function. Okay, now a specific case, let's say, right, let's say there are only two values of xi's for which f of x is same. Okay, in that particular condition. For every other case, for every other case, let's say, okay, f of x is something else. Let's say f of x is, uh, let's say, for f of x1, for f of x2, okay, it's w, right? So for other case, I'm not worried. Only because they are different values. Only for two values, it is common. The function value is common. So in that case, what would be my psi3 will be? Psi3 will be, now the summation of x disappears because only two values it is common. So z belongs to 0, 1 tensor n minus 1 to the power of x into x1 into z. Okay, and what is the value? Which is zw. Okay, and plus minus 1 to the power of x2 z zw. So this is the function. Okay, so in short, we might missed 1 by 2 to the power of n here, so which can come out, okay, 1 by 2 to the power of n summation over z 0, 1 tensor n minus 1 to the power of x1 into z plus minus 1 to the power of x2 into z, okay, which is z tensor w. So this is my psi3. Now I will only query what is the state of the z. Okay, what is the state of z? I'll only query, right? So as I know, the probability amplitude for w must be same because only those two values are coming non-zero. Okay, so which means what I can conclude here is minus 1 to the power of x1 into z is equal to minus 1 to the power of x2 into z. Okay, x2 into z. Okay, so when it is this possible, this implies x1 into z is equal to x2 into z. By the way, dot products are all modulo 2. Okay, modulo 2. So this relation, right? So I got two solutions. For example, here, okay, uh, only two numbers we assumed it we will get, but let's say there are multiple cases. In that case, what we will have, we'll be getting not just two equations, we'll get many equations. What are those equations would be? Those equations could be, okay, for generalized case, we just took only two, for two pairs the f of x value is common. Let's say for m cases, let's say for m cases f of x values are same. So in that case, what I'll get? I'll get a multiple equations. What are those equations? Those equations I can write now as, okay, instead of writing in x1 and z, I'll write in terms of s. You know why? x1 plus x2 is actually s. Okay, right? So once I add, okay, once I add this equation to above, what I can show, this is simply z into s is equal to 0. Okay, so for a generalized case, for m situation, what I'll have multiple equations. Z1 into s is equal to 0, z2 into s is equal to 0, and so on. Zm into s is equal to 0. So this many different number of equations I will be getting. So here m equations and n variables. Okay. So this system of m equations, m variables, which can solve efficiently using classical methods using some Gaussian elimination, could be solved using Gaussian elimination method. Okay, right? So, right? So, what important thing is we will only analyze what is the output. What is the output at the query part? So, circuit, where is the circuit? Let me show you. Yeah. So the measurement only happens at the query part, and by knowing the query output, we can make out what is the S. Okay. So, right. Okay. So now Alice prepares at the left hand side end her queries and sends to Bob. Bob calculates his functional value, sends back to Alice. Alice asks n Hadamas and makes a measurement, and from the measurement she will make out what is the yes, that specific shift function or yes function in one shot. Okay, so what I will do now, I'll quickly show you the implementation in the Q inverse. Okay, so let's see. I have it here. Let me log in. Okay, right. Okay, so okay, so let me log in by exiting the share. Okay, 1 minute. Okay, right. So let me share using some other screen. Yeah, so I just want to log in so that password cannot be revealed. Yeah, I'm logged in. Okay, so let me share screen now. Right. Yeah. Now I have a Q inverse logged in. Go to the algorithms. So the bottom left we have Simon's algorithm. Okay, let's say I have a bit string, 2 qubit bit string, which is, let's say, 10. 10 is my yes. So load the circuit. So what is the corresponding circuit? So this is a corresponding circuit, what you see. Okay, so the Q0 and Q1 is the queries, and Q2 and Q3 is ancillas. And for queries, we have two Hadamard's, and my my oracle function is having, okay, oracle function is having what? It is having 3 C0s, and after that there are two Hadamarts which were used in the initial, the same way I have. So now I have a measurement made at Q0 and Q1. So I should be getting the output. Okay, the probability output is a state vector. Yeah, here you see 0 1. Okay, this is the state 1 0 in a reverse fashion. That is the one which having different color. From there we will make out. Okay, so let me go further and implement for higher number algorithms. So let me go for 4 qubit, 4 qubit, and the bit string is, let's say, all ones, 1 2 3 4, and load the circuit. Yeah, so all the circuit, Okay, so there is only circuits fewer than 6 qubits. Yeah. Okay, so 6 qubits in the sense 4 plus 4, 8. No? So it can't go more than 4. So what I will do, manage. Okay, let me reduce maybe 3. Okay, so this is also 3. Okay, and here do I get? Yeah. Okay, so what is the state? I would not, yes, I had put. So let me go back and do it from the start. Algorithms, 3 qubits, all of them are ones. Yes, bit string. Okay, load the circuit. It must work. Hopefully it should working. Okay, and the probability distribution, let me go to state vector. Yeah, so there are multiple cases with triple ones. So which one? I think we should by analysis we should be able to get that. Okay, right? So this is the Siemens algorithm implementation, and we need to use a Gaussian elimination method. Okay, after this, so then only we can figure out what is the S value. Okay, right? So let me go back. So if I had to summarize, okay, right, steps, right, okay, the steps of Siemens algorithm. Number one, Alice prepares her queries, okay, using n 0 qubits in n states and operates n Hadamard's and prepares, okay, step 2, prepares equally probable, okay, equal probable, okay, 2 to the power of n states, which are summation over, okay, 2 to the power of n, x belongs to 0 comma 1 to the n, right? These are the states, and she prepares, sends to Bob. Bob receives, okay, and uses Ancilla's 0 n and operates oracle function on, okay, let's say on Alice's state, and returns the output. Okay, now Alice operates or acts n Hadamards on query part and analyzes the query amplitudes, okay, and Alice obtains yes by solving the equations satisfying, okay, the amplitude outputs. So what are those? Z into Z is into S equal to 0. Okay, those equations are solved, and from there she gets yes. So this is the Siemens algorithm. So this is how you should able to understand. I have given the PPT with the circuit wise hints. So please, the circuit is slightly different here in the PPT. Maybe that you can ignore. Hadamard's you can ignore. It's not, measurement also you can ignore. At the query part, only you can have at the, sorry, at the, uh, yeah, the next circuit is having, yeah. So this is a Simmons algorithm circuit. So measurement is not required again at the ancilla, right? So you would be getting multiple equations. From there, you have to find the S value, S bit string. Okay. So classical post-processing Gaussian elimination method from the matrix. Okay, right? And see, this is just a trend of quantum algorithms. Just to summary for you, right? From 1900, how the quantum computing is developed, where exactly Simon is lying here. If you just to see, okay, somewhere. Wait a minute, 90s, 94, Grover, sure, 85, somewhere here. Okay, somewhere at this point. Okay, Tevesinjo criteria, quantum computing. Fine. So why it matters? First, exponential quadratic speed up. It's a blueprint for Shor's algorithm. Okay, and it is a foundation of hidden subgroup problems. Okay, it shows interference and parallelism. Okay, at a quantum level. Fine. So I just stop at this point. Okay, so I have discussed all the four algorithms: Dutch, Dajouisa, Bernstein-Swajrani, and Simon's algorithm. So those who are interested can just go to this Q inverse and implement all the four algorithms for multiple cases by just picking what kind of a function you want to search. Okay, what kind of a bit string you want to search. Okay, so that you can do, right? So a detailed uh, how is this Q inverse is working, which will be discussed by CDAC people, I think, in later in your sessions. So this is all for today. So if there is any questions, please ask. Otherwise, we can wind up for today. Okay. So when it comes to understanding Simon's algorithm, I'll be saving my hand notes. So this is more elaborative. Okay. And what kind of a notes I have used for that, that also I will share. Okay, Simon algorithm. Okay, so you people can use that. Fine. Okay, so there is a question here. Let me see. Okay, can you brief how Ancilla is helping to obtaining the z s is equal to 0? If possible, please give some analogy. Okay, right. So a specific case would be much easier to understand. Okay. Okay, let me pick a specific situation. Do I have some example in my notes somewhere? I don't have. Ah, okay, so okay, so from here itself, I think you can just take. Let's say the only two numbers which are matching. Let's say, uh, okay, for let's say x naught and x6 are the only two. Even for every other case, okay, for every other case, I'm not getting f of x's are common. Okay, right? So which means here itself, here itself, which means I have x0 into z is equal to x6 into z. That is what I will get. Okay, right? Just we saw earlier x naught plus x6 is yes. Okay, so in the addition modulo, subtraction is nothing but addition. So you can send the right hand side to the left hand side. Okay, what happens? It becomes x naught plus x6 into z is equal to 0. Okay, what is x naught plus x6? Which is yes. S dot z is equal to 0. Okay, so basically knowing the z, okay, knowing the z for corresponding z, for, let's say, right, I have, okay, let's say my z state is, let's say it's a 110. This is my dead state. Okay, so what I got the equation, my equation is s dot z is equal to 0, which means s1 into z1 plus s2 into z2 plus s3 into z3 is equal to 0. By the way, I just got to know what is z1, z2, z3. Z1 is 1, z2 is, okay, z2 is 1, z3 is 0. Okay, from there I can make out what would be the s1, s2 and s3. By the way, it's not easy because when you substitute z1, z2, z3 here, what happens? I'll only get s1 plus z. Okay, s1 plus s2 is equal to 0. Okay, s1 plus s2 is equal to, it's addition modulo by the way, s1 plus equal to 0, which implies s1 and s2 both can be zeros, or s1 and s2 both can be 1. Okay, right? So in that way, we need to, by elimination method, we should get what is the corresponding s. Okay, and here I have no information of s3 because s3 is just ignored because z3 is 0. So for that I need one more equation. So in this way you will be able to find what is the corresponding s. What is the corresponding s? Okay, right? So for example, my s would be something like, if s is 1 1 1, okay, in that case, if the s is 1 1 1, does this satisfy this equation? Yeah, I think it satisfies. 1 into 1 plus 1 into 1 plus 1 into 0 is equal to 1 plus 1 is 0. Okay, yes, this is a one possibility. There is also one more possibility. What is that one more possibility? Is s equal to 110. So even in that case also will satisfy 1 plus 1, 1 plus 1, 0 into 0 is 0. This is also easy. Okay, so among these two, I'll have, yes, there is another possibility. What is the possibility? All s's are zeros. Even in that case also I'll get. This is the most obvious solution. Okay, so for finding all this case, I need a multiple equations which only will get for, will get exactly, we solve the entire all these equations in one go. Okay, I'm sorry, I think s1, s2 and s, yeah, yeah. Okay, right, I hope that makes sense. Okay, Rohan, yes, thank you. Okay, so what is the other question? In research aspect, how, where can we utilize these algorithms? Yeah, so it is basically in the case of cryptography only. Okay, let's say Bob has to convey a one-time pad, or some, let's say Alice and Bob has to communicate, but they don't know, they can't see each other. But Bob has a code. in form of yes, but he can't publicly reveal that yes. Okay, so Alice what does? Alice creates her quantum state, sent to Bob. Okay, Bob finds the value of the function using that quantum state, sent back the value back to Bob. So this is a quantum channel. Okay, so nobody can take that information and get something out of it. Okay, so if something is done, quantum formation or quantum gets disturbed, so that they can easily notice. So that's why using a quantum channel or quantum information is more secure. So by doing this, Alice can find out what is the yes. It's a bit string. Okay, P initially is given an instruction to Bob, please use the F created out you created using some fixed yes. Okay, now whenever Alice wants to communicate, she just sends a quantum state, gets back the result. From there she finds a yes or yes matching, they do the communication further. It's like a code word. Before talking to some agent, right, a spy agency would ask the agent to reveal what is the code. So same here, in the cryptography it can be used. Okay, fine. So that's about the Simon's algorithm. Okay, right. So please go through my hand notes, and I will also share one PPT with one working draft from some seminar. Okay, right. You people can read through and understand if you are not understanding my lecture notes. Fine. I'll stop at this point and thank you very much. Okay, and if there is any more sessions I would be taking, so I'll meet you that time. Okay, right. So I'll upload all the notes I'm just doing till date. Yeah. Yes, thank you, sir. All the kind words, everyone. So it is
Thank you
slightly,
so much.
yeah, slightly too much to a lot of mathematics. So I would urge you people to just go through this session recordings if you find, or you can read through the notes which I'm submitting. Okay.
Yes, sir.
Yes.
Thank you, sir. Thank you so much.
Yes, Satyam sir.